Welcome back, everyone. Hello. I am doing the Unit 3 test study guide, selected answers for the review for the final exam. The first problem that I'm going to look at is f of x equals x squared plus 5x plus 4 divided by 3x squared minus 3x minus 6. What I'd like you to do here, the first thing you need to do is factor the top and factor the bottom. So the top factors into x, two numbers that multiply to 4 and sum to 5 with the signs that are the same. Then in the bottom I factor out a 3 and I get x squared minus 3x minus 6, which means that in the bottom I get 3 times, that would be x, two numbers, oopsies, I didn't factor out the 3 and all of that. Two numbers that multiply to -1 and sum to -2, and that is 2 and 1, -2 and +1. Okay, so I'm just going to cross that out to show that that's no longer the denominator. The denominator has been factored. Many of you commented that you can cancel these. When you cancel, you get a removable discontinuity where x equals -1. What that means is that where x equals -1, there's a hole in the function. But I can still plug -1 into the remaining parts of this function. And when you do that, you get that the function is equal to -1/3. So there is a removable discontinuity at -1 comma -1/3. You'll notice that the other value that's in the denominator, we have to look at to find out where the function is undefined. So there's a vertical asymptote where the function is undefined. In other words, where x equals 2. So that's where the vertical asymptote is, x equals 2. So I'm going to draw that vertical asymptote. And then because of my knowledge of rational functions, or if I wasn't sure, I could plug in a couple of numbers. What I find is that the function follows a pattern something like this, and then something like this. Let me make this part just a little bit neater and tidy that up. Okay, but there we find that there's a horizontal asymptote here at y equals 1/3, and I know that from the numbers that are out in front. There's a 1 out here, and there's a 3 here. The function has a horizontal asymptote at y equals 1/3. We never talked about slant asymptotes, so don't worry about that. When we look at the domain of this function, it's all real numbers, such that x cannot equal -1 or 2, and the range is all real numbers, such that y cannot equal -1/3 and +1/3. All right. When we go to the x-intercepts, we need to use the calculator again to, this is where y equals 0, and we can do second calc. Let's see if I can get that app up. We can do second calc, and y equals, we'll type in the equation, which is x squared, I think that was, what was it? X squared plus 5x plus 4. X squared plus 5x plus 4, parentheses, divided by parentheses, 3x squared minus 3x minus 6. And when we graph that, there it is. When we hit second calc and we want to find the 0, we bring, it's a little bit different with your calculator and the iPad, but I think if we scroll over to where the y values go positive, okay, hit enter, and then we'll find the right bound. So we'll go to where the y values go negative now. Closer to 0, there we go. Right bound, enter, enter. And I get that there's a 0 at x equals -4. Oh, well, that makes sense, because look at this. If I plug -4 in right here, that makes the function equal 0. Should have figured that out a long time ago. -4, comma 0. Okay. The y-intercept is where x equals 0. So if I plug 0 into this function, like 0, 0, if I plug 0 in for x, I get 4 over -6. I get -2/3. So the y-intercept is at 0, comma -2/3. Okay, this function is never increasing, and it is decreasing over the interval from of all real numbers, I'm going to say, except where x can't equal except -1 and 2. You could say that in a number of different ways. There is a hole at that removable discontinuity, -1, comma, -1/3. Okay, in the interest of time, moving on. And I want to now talk about synthetic division and dividing polynomials. So I am going to divide this polynomial by using synthetic division, and I'm putting not the factor, but the root or the 0 right there, and then the coefficients of the polynomial here. I need to make sure that there aren't any gaps in the exponents, that they decrease in order, 4, 3, 2, 1. And then my synthetic division is bring down the first coefficient. Multiply, going this way, put the next number here, and add as I go down to fill in the numbers. 4, 24, 2, 12, -3, -18, and I've got 2 left over. I know that x minus 6 is not a factor of f of x. I'm just going to call that f of x because it has a remainder. So the quotient here, when we do division, is 2x cubed plus 4x squared plus 2x minus 3 plus 2 over x minus 6. That's adding my remainder. My exponents decrease by 1. Since I started with to the 4th, my answer is going to end with a cubic as a cubic function. Okay, as we move on here to number 20, I ask you to use the factor theorem to determine which binomials are factors of the function below. So I could use x equals -1, x equals +4, and x equals -3. Let's just go down the line. -1, we're checking to see if that is a factor of this polynomial f of x. 2 comes down, and then I'm doing multiplication diagonally, and I'm adding. That would be -6. That would be +6 here. And then, let's see, that should work. Oopsies, I made a mistake. Thanks for catching that. What happens when you multiply -1 times 2 is -2, and then you get -5, and then you get 5, and you get -12. You get +12, you get 0. So yes, x plus 1 is a factor. I can continue to do synthetic division with the quotient, which is the answer I get when I divide. Now I can plug in the next factor, possible root, which is 4, and bring the 2 down. That's 8, 3, 12, and 0. Now the last one, x plus 3, I could do synthetic division here and get 2, and then, bring down the 2, and then 6, and add that to 9. That's not, that's going to be -3, excuse me, -6 and -3. And that is not going to work. So -3 is not a factor, but, -3 is not a root, and x plus 3 is not the factor, but x equals -1 and x equals 4 are roots of this polynomial. Moving on to 25 now. Use the rational zero theorem to list all the possible rational zeros. That's going to be the factors of the last term divided by the factors of the first term. And so I'm looking for the factors of 28 divided by the factors of 2. And so I could list all of those as 1, 2, 4, 7, 14, 28, 7 halves, and I believe that covers it. And that's plus or minus all of those. Moving on to 31, now I ask you to put all this together. Find the zeros and give the complete factorization of the function. We'll use the rational zero theorem in division when necessary and simplify if we end up having complex solutions. Okay, so in this first one, I have no common factor. What I have to do is see where, well, I have a couple of options, I guess. I could start to factor this, see if I can do factor by grouping, or I could list the possible rational zeros. That would be the factors of 6, which would be 1, 2, 3, and 6 over the factors of 5, and start to do synthetic division there. I'm going to guess a -1 here. So when I try -1, I bring down the 5, the 12, the 1, and the -6. Let's see how this works. -5, that would give me 7. If I put 7 here, I get an 8. And -8, that is not going to work. So -1 is not a factor. -1 is not a root. Let's try 1. 5, 12, 1, -6. Bring this down. That would be 5. That would give me 17. 17. Not working here. Let's see. So if I start to get stuck and I don't feel like doing all of this division, I can use the calculator to help me. So I can type in into this 5x cubed plus 12x squared plus x minus 6. Plus 12x squared plus x minus 6. Enter. I can graph it, get a look at it, and see where it looks like these roots are. It's hard to tell on the scale, but if I can move the cursor over here, let's see. Looks like where x equals -1. Oh, it's funny how that synthetic division didn't work, but I could try it again with -1. Let's see if I can, there we go. And maybe here at x equals -4, and here at x equals, not sure, let's see. Still not quite sure how to use this program on the calculator, but let's try -1 again. It's odd that that didn't work because I'm pretty sure that that is in fact a root. 5, 12, 1, -6. That's 5, that's -5, that's 7, that's -7. There we go, I just made a mistake before. That's -6, and when I multiply those I get 6. So thanks for being patient with me. Now, let's do synthetic division with the next factor, which is, let's see, well, let's do this. 5x squared plus 7x minus 6 equals 0. So I can now factor this. It doesn't even have to equal 0, but I can factor this now. I'll factor it using product sum. So two numbers whose product is 5 times 6, which is 30, and whose sum is 7. That's 10x and 3x, and it would be plus 10x minus 3x and 5x squared. So I didn't want to do synthetic division, but I got to a point where I could factor, and I can factor out a 5x here, and this becomes x plus 2. Factor out a -3 here, and this becomes x plus 2. So my two factors are 5x minus 3 and x plus 2, which means that if I set both of those equal to 0, I have one root that is x equals -2, and I have another root that is x equals 3/5, and then my last root I found through synthetic division is -1. Those are the three roots here. Okay, the next one is multiplicity. So let's talk about the multiplicity where there's a 0. There's a 0 everywhere there's a factor. There's a 0 at x cubed, which would give me a 0 at the value of 0. There's a, when I set 2x minus 3 equal to 0, that means x equals 3/2. And then x plus 7 set equal to 0, that means where x equals -7, there's going to be a root as well. X cubed has multiplicity of 3 here, and the effect is that that crosses the x-axis. At 3/2, it has multiplicity 2, which means that it's just going to touch and turn around. It's going to be tangent to the x-axis at 3/2. And then at -7, it has multiplicity 5, and so it crosses the x-axis, where x equals -7. So the polynomial ends up having a total of 10 roots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's that. Okay, moving on now to 39. We need to use the number line and then test intervals. And so I want to know where this function is positive and above the x-axis. I'm going to do this one next in a separate video. So stay tuned for part 2 of the Unit 2 test.